And at present session, we have the session chair, Dr. Ravindra S. Hegde sir. Sir is professor in the Department of Computer Science, Central University of Karnataka, Kalburgi. Sir has 27 years of experience in teaching, and the research areas are artificial intelligence, machine learning, computer vision. Sir has published 81 research articles, 7 books, 40 book chapters, and 60 conference proceedings. And Sir has awarded Professor Satish Dhawan Young Engineering Award by conference proceedings, Karnataka State Council for Science and Technology, Government of Karnataka in the year 2023. And Anveshana Acharya Award by Bharat Education Excellence Awards in the year for the academic year 2023 to 24. And Sir has visited abroad, USA, UK, Australia, Malta, Dhaka, Bangladesh, Hong Kong. So with this brief introduction, I'd like to call Dr. Ravindra Hegde sir to hold the session.
Okay, so he will be delivering on. Good morning all. So the first session is by Mr. Shashidhar Kallur. He is a technical leader in integration landscape, Workday integration manager, Camping World, Hybrid USA. So he is going to deliver the talk through online mode. First of all, I would like to welcome Mr. Shashidhar Kallur. He is online? Okay. So he is going to deliver a pre-recorded video. So the talk will start.
Currently serving as the Workday Integration Manager at Camping World. Good morning everyone. My name is Shashidhar Kallur, currently serving as the Workday Integration Manager at Camping World, Buffalo Grove, Illinois, USA. Today I am honored to present my research at the International Conference on Mathematical Analysis and its Applications. My talk today is focused on wavelets and their application in science and engineering. In this presentation, I'm going to discuss the fascinating world of wavelets and their historical development and their various applications across different domains such as image processing, signal analysis, and numerical analysis. I'm looking forward to sharing insights on how wavelets transforms provide efficient ways to analyze waveforms and solve differential equations, particularly highlighting the hard wavelets-based numerical methods for thermal behavior analysis. Thank you for joining me today, and I hope you'll find this session insightful and engaging. Let us look at the outline for today's talk. We will begin with the overview of wavelets, followed by a discussion on that historical development of a wavelet theory. Then we will delve into the time versus frequency domain analysis, Fourier analysis, and compare Fourier and wavelet transforms. We will also cover wavelets analysis and its typical application, concluding with references. Let's start with a brief overview of the wavelets. A wavelet is essentially a small wave. Wavelet transforms converts a signal into a series of wavelets, providing a way to analyze waveforms that are bounded in both frequency and the durations. This allows signals to be stored more efficiently than by using Fourier transforms and can better approximate real-world signals, especially those with the sharp discontinuities. Wavelet theory has evolved significantly over time. Before 1930, Joseph Fourier laid the foundation with his theories of frequency analysis. In 1930, scale varying basis functions were used to compute the energy of functions. From 1960 to 1980, researchers like Udo, Weiss, Ronald, Kaufman, Grossman, and Morlett contributed further. In post-1980, wavelet application expanded with the work of Stephen Mallet and the Mayer and Ingrid. Mathematical transformations are essential for extracting additional information from the raw signals. The most popular transformation is the Fourier transformation, which helps in understanding the frequency components of a signal. However, we also need One. My name is Shashidhar Kallu. In post-1980, wavelet application expanded with the work of Stephen Mallet and the Mayer and Ingrid. Mathematical transformations are essential for extracting additional information from the raw signals. The most popular transformation is the Fourier transformation, which helps in understanding the frequency components of a signal. However, we also need to consider the limitation when dealing with the non-stationary signals, where frequency components change over time. Frequency analysis involves examining the frequency spectrum, which shows the spectrum components of a signal. The Fourier transformation is a widely used method for determining the frequency content of a signal, telling us how much of each frequency exists within it. Signals can be stationary or non-stationary. Stationary signals have constant frequency content over time, while non-stationary signals have frequencies that change over time, like a chirp signal. Understanding whether and when the incident occurs in transporting signal, for example, requires time representations. So stationary signals and non-stationary signals. The top row of the slide represents stationary signals. The time domain and the frequency domain demonstrate constant patterns. The signal frequencies components remain constant over time, as evidenced by the stable frequency spectrum, whereas in non-stationary signals, in context, the bottom row showcase the non-stationary signal. The time domain plots reveals variation in the signal's amplitude and frequency over time. The frequency spectrum also changes, reflecting the time-varying nature of a signal. As shown in the slide, chirp signals exhibit distinct patterns in the time domain. The two examples demonstrate signals with increasing and decreasing frequencies. The waveform gradually compresses or expands over time, reflecting the changing frequency content. Surprisingly, Fourier transformation of both chirp signals appears identical. This is because the Fourier transformation provides information about the frequency components presenting in the signal, but it does not reveal when these components occur in time. The Fourier transformation, a double-edged sword. The Fourier transformation is a powerful tool for analyzing the frequency content of a signal. It breaks down a signal into constituent sinusoidal components. However, it is a critical limitation. It provides information about the frequency components present in the signal, but not when those components occur in the time. So the challenge of non-stationary signals. Many real-world signals such as speech, music, and biological signals are the non-stationary, meaning their statistical properties change over time. The Fourier transformation is ill-equipped to handle such signal effectively. The need for time frequency analysis. To overcome the limitation of the Fourier transformations, we require techniques that can simultaneously analyze both the time and frequency characteristics of a signal. This is where time frequency analysis comes into play. The short time Fourier transformation, STFT. It is one of the earliest solutions to this problem was the STFT. And the STFT divides the signal into short, overlapping frames and applies the Fourier transform to each frame. This provides a time frequency representation of the signal. The short time Fourier transform, STFT, introduced by Dennis Gaber in 1946, analyzes a small section of a signal at a time by widowing the signal. However, it faces the dilemma of resolutions. Narrow window offer poor frequency resolutions, while wide window offers poor time resolutions. The dilemma of the resolution. The STFT employs a fixed length window to analyze the signal. This fixed window size presents a fundamental trade-off. The narrow window, provides a good time resolution, allowing us to pinpoint the occurrence of the event in time, but at the cost of poor frequency resolutions. Wide window. So it basically offers a better frequency resolution, enabling us to accurately identify frequency components, but at the expense of poor time resolution. The Heisenberg uncertainty principle in action. This trade-off is a direct consequences of the Heisenberg uncertainty principle, which states that there is a fundamental limit to the precision with which certain pairs of physical properties of a particle, such as positions and momentum, can be known simultaneously. In the context of STFT, this translates to a trade-off between time and frequency resolution. To overcome with the resolution problem of STFT, we use multi-resolution analysis, called as MRA, with the wavelet transforms. This approach analyzes signals at different frequencies with different resolutions, offering good time resolutions at high frequency and good frequency resolution at low frequencies. The wavelet transform splits into signal into different frequency bands, providing information on what frequency band exists at what time intervals. This multi-resolution approach is particularly useful for analyzing signals with varying frequency components. The continuous wavelet transform, we call it CWT, uses a mother of wavelets to generate other wavelet functions through a dilation and translation. The wavelet is scaled and shifted across the signals to analyze its frequency components over time. As shown on the slide, the CWT is a continuous time signal. XT is defined as CW2 into bracket AB is equal to 1 square root A into integration XT into psi into T minus A divided by 2A into dt, whereas A is a scale parameter, whereas the B is a translation parameter, whereas the psi t is a mother wavelet. So the mother wavelet psi t is a fundamental building block of the CWT. It is a localized oscillating function with specific parameters. By scaling and translating the mother wavelets, we generate a family of wavelet functions that form a basis of representing the signal. So what is scale? In essence, a scale refers to a level of detail we examine with a signal. My name is Shashidhar Kallu, currently serving as the work. It provides good time resolution, allowing us to see characteristics of a signal. This is where over a time. Frequency analysis involves examining the frequency spectrum, which shows the spectrum components of a signal. The Fourier transformation is a widely used method for determining the frequency content of a signal, telling us how much of each frequency exists within it. Signals can be stationary or non-stationary. Stationary signals have consistency and each level time resolutions at high frequencies and better frequencies resolution. Computing this CWT involves several steps, starting with wavelet is scaled and shifted across the signals of the event in time, but at the cost of poor frequency resolutions. Wide window. So it basically offers a better frequency resolution, enabling us to accurately identify frequency components, but at the expense of poor time resolution. The Heisenberg uncertainty principle in action. This trade-off is a direct consequences of the Heisenberg uncertainty principle, which states that there is a fundamental limit to the precision with which certain pairs of physical properties of a particle, such as positions and momentum, can be known simultaneously. In the context of STFT, this translates to a trade-off between time and frequency resolution. To overcome with the resolution problem of STFT, we use multi-resolution analysis, we call as MRA, with the wavelet transforms. This approach analyzes signals at different frequencies with different resolutions, offering good time resolutions at high frequency and good frequency resolution at low frequencies. The wavelet transform splits into signal into different frequency bands, providing information on what frequency band exists at what time intervals. This multi-resolution approach is particularly useful for analyzing signals with varying frequency components. The continuous wavelet transform, we call it CWT, uses a mother of wavelets to generate other wavelet functions through a dilation and translation. The wavelet is scaled and shifted across the signals to analyze its frequency components over time. As shown in slide, the CWT is a continuous time signal. XT is defined as CW2 into bracket AB is equal to 1 square root A into integration XT into psi into T minus A divided by 2A into dt, whereas A is a scale parameter, whereas B is a translation parameter, whereas the psi T is a mother wavelet. So the mother wavelet psi T is a fundamental building block of the CWT. It is a localized oscillating function with a specific parameters. By scaling and translating the mother wavelets, we generate a family of wavelet functions that form a basis of representing the signal. So what is scale? In essence, a scale refers to a level of detail we examine with a signal. It's akin to zooming in or out on a map. A large scale provides a more detailed view, while a small scale offers a broader overview. In the scale and signal manipulation, dilution when a scale parameter S is greater than 1 into bracket S minus S 1, the signal is dilated or stretched. This provides a zoomed in perspective highlighting the fine details. Whereas the compression, conversely when S is less than 1, the signal is compressed or shrunk. This offers a zoomed out view, emphasizing the overall shape or trend. Scale and frequency relationship. There is an inverse relationship between the scale and frequency. Whereas the low frequency, it corresponds to a high scale, providing a non-detailed global view of the signal spanning it entirely, whereas a high frequency corresponds to a low scale, offering a detailed view of the signal, focusing on short time segments. Computing this CWT involves several steps, starting with the placing the wavelet at the beginning of the signal and setting the scale to 1. The wavelet is then multiplied by the signal and integrated over all the times. This process is repeated for different scales and shifted to obtain the CWT. The CWT formula. Let's start with the mathematical definition of the CWT. As you can see on the slide, the CWT of a signal XT is defined as CWTY into bracket T and S, whereas T represents time and S represents a scale. The formula involves convolving the signal with a scaled and shift version of the wavelet function psi T. Step-by-step computation. Now let's break down the computation of the CW into steps. Step 1, initialization. We begin by placing the wavelet of the beginning of the signal. The scale parameter is S is set to 1, representing the most compressed wavelet. Step 2, multiplication integration. Here the wavelet function at scale 1 is multiplied with the signal, and this product is then integrated over all times. Finally, the result is multiplied by the scaling factor of 1 square root of S. Step 3, shifting. The wavelet is shifted to the next time point. T is equal to T plus delta T. The transform value is calculated at this new time and scale. Step 4, repetition. Step 2 and 3 are repeated until the wavelet reaches the end of the signal. With the step 5, scaling. The scale parameter S is increased by a small volume. the entire process, it means step 1 to 4, is repeated for the new scale. Then step 6, row formation. The computation for a given scale fill a single row in the time scale plane. The last but the least is step 7, CWT completion. The CWT is obtained by repeating step 5 and 6 for all the desired scales. The resolution of a time and frequency. The Fourier transform offers a better time resolutions at a high frequencies and better frequencies resolution at a low frequencies, addressing the limitation of a STFT. This adaptive resolution makes it suitable for analyzing signals with varying frequencies components over time. So let's start by understanding what time frequency resolution means. As you can see on the slide, time frequency resolution refers to the ability of a signal analysis method to simultaneously localize both the time and frequency components of a signal. The time frequency signal is a visual representation of the concept. The x-axis represents time and the y-axis represents a frequency. Each point in the plane represents a combination of a time and frequency. As you can see in the slide, when we use the short window length, we achieve better time resolutions. This means we can accurately localize events in time. However, the frequency resolution is poor, meaning we cannot actually accurately distinguish between different frequencies. So better frequency resolution and the poor time resolutions. Conversely, when we use a long window length, we achieve better frequency resolutions. This means we can accurately distinguish between different frequencies. However, the time resolution is a poor, meaning we cannot accurately localize events in time. Comparisons of a transformation. So Fourier transformation offers several advantages over Fourier transformation, particularly in handling non-stationary signals. While Fourier transforms provide global frequencies information, wavelet transforms offer localized time frequency information, making them more versatile for a real-world application. So let's begin with the Fourier transformation. As you can see on the slide, the Fourier transforms takes a time domain signal and converts it into a frequency domain. This allows us to analyze the frequency content of the signal. However, the Fourier transform does not provide any information about when specific frequencies occur in the signal. Shorter Fourier transformation. To address the limitation of the Fourier transformation, we can use the STFT. The STFT divides the signal into short segments and performs a Fourier transform on each segment. This provides a time frequencies representation of the signal, allowing us to analyze both the frequencies content and when those frequencies occurs. However, the STFT has a fixed time frequency resolutions, which means that it cannot accurately represent signals with rapidly changing frequency content. The wavelet transform is a more flexible approach to time frequencies analysis. It uses a set of basis functions called wavelets, which are localized in both time and frequencies. This allows the wavelet transform to adapt its resolution to the signal being analyzed. The wavelet transform can provide a better time resolution for a high frequency components and a better frequency resolution for a low frequency components. Comparison. Let us summarize the key difference between these techniques. The Fourier transform provides information about the frequency content of the signal, but not when those frequency occurs. Whereas the STFT, shorter Fourier transformation, provides information about both the frequency content and when those frequency occurs, but has a time fixed frequency resolutions. So, whereas the wavelet transformation provides a flexible time frequency represents that can adapt to a signal being analyzed. Discretizing the CWT is necessary for practical applications. The discrete wavelet transform DWT provides a sufficient information for analysis and synthesis, reduces the computation time, and is easier to implement. It decomposes the signal into coarse approximation and detailed informations. Multi-resolution analysis (MRA) overcomes the limitation of Heisenberg uncertainty principle by providing a good time resolution at high frequencies and a good frequency resolution at low frequencies. This is particularly useful for natural signals with varying frequencies content over different durations. The subband coding algorithms halves the time resolution and doubles the frequency resolutions. This approach decomposes the signal into different frequency bands, each containing a subset of an original signal's frequency contents. Let's start by understanding how subband coding helps the time resolutions. As you can see on the slide, this is achieved by simply reducing the number of samples in the original signal. By taking one half of the samples, we effectively reduce the time resolution by half. Now let's see the subband coding double the frequency resolutions. This is where the subband decomposition comes into play. The original signal is passed through a series of bandpass filters, each with specific frequency range. This process divides the frequency spectrum of the signal into multiple subbands. Subband decomposition. It is a process can be visualized as a tree structure. The original signal is the root of the tree, and each level represents a further division of the frequency spectrum. At each level, the signal is split into two subbands using a bandpass filter. So, benefits of a subband coding. Subband coding offers several advantages. One is improved time resolution. By reducing the number of samples, we can achieve fast processing and a low storage requirement, and that improved frequency resolution, whereas the subband decomposition allows us to analyze different frequencies components of a signal with a higher precision. And whereas effective coding, subband coding can be combined with the compression techniques to further reduce data size. Application. Subband coding has a wide range of applications including audio and speech processing, whereas it improves the quality of compressed audio and speech signals. Image and video processing, whereas enhancing image and video compression and analysis. Medical imaging, it improves the resolution of a clarity of a medical images. And last but not least, acoustic, nuclear engineering, signals and image processing, and more. Typical applications include identifying pure frequencies, denoising signals, detecting discontinuities, and compressing images. Multi-resolution analysis and wavelet spaces. Wavelets are powerful mathematical tools used for various applications in science and engineering. They allow for multi-resolution analysis, which helps in break down complex signals into simpler components for easier analysis. The continuous wavelet transform, the CWT, is a versatile tool for signal decompositions. One of the commonly used wavelets is the Mexican hat wavelet, which we will use as an example to illustrate the process. As shown in the image, the wavelet function denotes as psi t is a localized oscillating function. It serves as the basis of the wavelet transform. The specific shape of the wavelet influences the analysis results. The continuous wavelet transforms of a signal ft is defined as WAB into A is equal to 1 square root A integration ft into psi t minus b divided by a into dt, whereas a is the scale parameter controlling the dilation or compression of the wavelet, whereas b is the translation parameter controlling the shift of the wavelet. Psi t is the mother wavelet. So the CWT coefficients WAV represents the correlation between the signal and the scale and the shift wavelet. By analyzing these coefficients, we can extract the information about the signal's frequency, content, and the time localization. Understanding the CWT, continuous wave transform. Basically, it is a mathematical techniques that decomposes a signal into a set of coefficients represent different scales and a translation of a mother wavelet. This provides a rich representation of the signal characteristics. So the Mexican wave hat wavelet. As an example, the image represents the Mexican hat wavelet, a commonly used wavelet function. Its a shape resembling a subverb is defined by the equation psi x is equal to 1 minus x squared into e exponential of minus x squared divided by 2. This wavelet is particularly useful for detecting the local features in a signal. The wavelet transform. The CWT of a signal ft is given by w f into a into b is equal to 1 square root a integration ft into psi t minus b divided by a into dt, whereas a is the scale parameter and the b is the translation parameter. The wavelet transform essentially involves convolving the signal with a dilated and shifted version of the mother wavelet. So visualizing the wavelet transform, the image demonstrates a real wavelet transform computed with the Mexican hat wavelet. The vertical axis represents the scale log 2 into s and the horizontal axis represents time t. The color intensity represents the magnitude of the wavelet coefficients. Darker regions indicate the higher energy content at a specific scale and location, whereas the lighter regions represent the lower energy content. The reconstruction using the CWT involves admissible wavelets that meet certain criteria, such as having a zero mean. However, in practice, discrete wavelet transform DWT are preferred as they preserve extract reconstruction. The Haar wavelet serves as a basis for L2 RL raised to 2. It is a simplet yet effective using averaging and differentiating for a signal analysis. The Haar wavelet function. As shown in the image, the Haar wavelet function is defined as psi t is equal to that 1 if 0 is less than equal to t is less than equal to 0.5 psi t is equal to minus 1 if 0.5 is less than equal to t is less than equal to 1 psi t is equal to 0 otherwise. So key points here is the Haar wavelet is a simple square pulse with a position and negative part. It is a mother wavelet for a Haar wavelet transform. So basis function, the Haar wavelet basis functions are generated by dilating and translating the mother wavelet. The basis functions psi m n into t is defined as the psi m n into t is equal to 2 raised to m minus m divided by 2 psi 2 raised to minus m2 t minus t, whereas m is the scale parameter and n is the shift parameter. The Haar wavelet enable multi-resolution analysis, whereas the scaling function acts as a low-pass filter. This analysis involves sequence of embedded approximation subsets and orthogonal components, facilitating efficient signals representing and processing. As illustrated on the slide, the Haar MRA consists of a sequence of embedded approximation subspaces, denoted as a Vj of the space L square R. These subspaces represents different level of resolutions. The key properties are functions in Vj are obtained by dilating functions in Vj minus 1 by the factor of 2. This implies that information at the coarser scale is contained within the finer scale. The scaling function phi t plays a crucial role in MRA. It generates an orthonormal basis of the coreset approximation space VO. The low-pass filter interpretation. The scaling function can be viewed as a low-pass filter capturing the low-frequency components of a signal. So the detail space. To capture the details lost in moving from the one approximation space to the next, we introduced the orthogonal complement spaces, denoted as a WJ. These spaces contain the high frequency information. Decomposition. Each approximation space Vj plus 1 can be decomposed into a direct sum of Vj and Wj, representing the coarser approximation and the detailed information respectively. Orthonormal basis. Within each information space Vj, we have orthonormal basis generated by dilation and translation of the scaling functions. So basic functions are that phi j k into t is equal to 2 raised to j by 2 into phi 2 raised to j into t minus k, whereas k is equal to z. Here we see an example of a hard wavelet multi-resolution analysis. It illustrates how signal can be decomposed and analyzed at various scales, making it a powerful tool for a numerical analysis. The HRA, the hard MRA. As illustrated on the slide, the hard MRA consists of a series of embedded approximation subspaces, denoted as a Vj of the space L square R. These subspaces represent a different level of resolutions. So key properties are that functions in Vj are obtained by dilating functions in Vj minus 1 by a factor of 2. This implies that information at a coarser scales is contained within the finer scale. The scaling function phi t plays a crucial role in MRA. It generates an orthonormal basis of a co-resist approximation space HO. The low-pass filter interpretation. The scaling function can be viewed as a low-pass filter recapturing the low-frequency components of a signal. The wavelet function psi t is derived from the scaling function and it generates an orthonormal basis of the detailed spaces Wj. High-pass filter interpretation. The wavelet function can be viewed as a high-pass filter capturing the high-frequency components of a signal. The image provides a visual representation of these equations. The scaling function phi t is decomposed into two scales and shifted version of itself. The wavelet function psi t is constructed by taking a linear combination of the same scale and shifted function with the different coefficients. So important of two scale relations. These equations are crucial for constructing wavelet bases and performing wavelet transformations. They form the foundation for multi-resolution analysis, which is essential for various applications in signal and image processing. The scale function. Let's start with the scale function denoted by a phi t. As shown in the image, phi t can be expressed as a linear combination of a dilated and a shifted versions of itself. Phi t is equal to hn phi 2t into 2t minus n, whereas the hn are the scaling filter coefficients. The equation signifies that the coarser representation of the function phi t can be obtained by combining scaled and shifted versions of itself. The wavelet function. The wavelet function psi t is derived from the scaling function through the similar relations. Phi t is equal to gn psi gn phi 2t minus t, whereas gn are the wavelet filter coefficients. Unlike the scaling function, the wavelet function captures the detail lost in the coarser representation. Orthogonal wavelets bases are crucial for accurate signal analysis. They involve solving two-scale equations and ensure orthogonality, which may require specific conditions to be met. Orthogonal basis for the subspace Vj, which represents a particular level of resolutions. The basis functions are denoted as a phi j k into t there. The two-scale relations of a scaling function is defined as the scaling function phi t satisfies the two-scale relationship. Phi t is equal to some equation hn phi 2t minus n. This equation states that the scaling function at a coarser level, phi t, can be represented as a linear combination of dilated and shifted versions of a itself at a finer level. Orthogonal wavelet functions. The wavelet function psi t is derived from the scale function using a similar two-scale relation. Psi t is equal to summation gn phi 2 t minus n. The coefficient gn are related to the scaling filter coefficient hn through the specific conditions. As mentioned earlier, finding a suitable filter coefficients hn is crucial. These coefficients determine the properties of a scaling and wavelet functions. Flexibility. While there is no unique solutions, we have a freedom to impose additional constraint to tailor the wavelet to a specific needs. So desired properties. These often include compact support for componential efficiency regularly for accurate signal representation and a certain number of vanishing moments for improved performances in various applications. So the Ingrid has pioneered a method to construct the wavelets with a minimal support length for a given number of vanishing moments. These wavelets, known as Topchi's wavelets, are widely used in practice. So the D2 wavelets, as shown in the slide, has two vanishing moment and minimal support. The corresponding scaling and wavelet functions exhibit of specific shape as depicted in the graphs. The filter coefficients. The slide provides the explicit formula for the scaling filter coefficients with the D2 wavelets. So the importance of this Topchi wavelets. Basically, these wavelets offer a balance between the time frequency localization and the regularity. Their compact support and vanishing moments make them suitable for various signals processing application, include image and signal processing, denoising and the feature extraction. Let's start by understanding how to find a set of coefficients that satisfy the scaling and wavelet equations. As you can see on the slide, we aim to find coefficients hn that fulfill these equations. It is important to note that the solution is not unique, allowing us to seek additional desirable properties for our wavelet functions. Desired properties. We can look for a wavelet with a compact support, meaning they are zero outside a finite interval. Additionally, we can strive for regularity, ensuring the wavelet function is smooth. Another important property is the number of vanishing moments, which determines how well the wavelet can represent a polynomial. Once we have defined the desired properties, we can proceed to solve the two-scale equations. These equations relate the scaling functions and the wavelet functions to their dilated and shifted versions. Solving these equations allow us to obtain the actual wavelet functions. An example of a wavelet construction method is a Topchi's wavelet. Topchi's wavelet are known for its compact support and a specified number of vanishing moments. They are widely used in various applications due to their desirable properties. Here we can visualize the Topchi's D2 scaling and wavelet functions. The scaling functions is a smoother and wider, while the wavelet function is more localized and oscillatory. It is important to note that most wavelets, including Topchi wavelets, cannot be expressed analytically, requiring numerical method for the computations. Fast algorithms for wavelet transforms starts with the initial coefficients and use relations between coefficients at different scales to obtain the desired constructions. This approach ensures efficient and accurate analysis. Let's start by understanding the decompositions and reconstruction process. As you can see on the slide, we begin with the signal represented by linear combination of a scaling function at the finite scale. Our goal is to express the same signal using a combination of scale functions at a coarser scale and a wavelet functions at intermediate scale. The key to efficient computation lies in the filter coefficient Hn and Gn. These coefficients relate to as coefficients at different scales through the equations shown on the slide. By convolving the coefficient at the finer scale, with these filters we can obtain the coefficients at the coarser scale and the detailed coefficients. Filter banks are used in a fast algorithms to facilitate the wave transfer process. They allow for efficient computations and a signal processing. As you can see on the slide, we are focusing on the key components, filter banks. They are digitally signal processing structure that composes a signal into different frequency bands. In the context of wavelets, they play a crucial role in breakdown a signal into approximation and detail at the different scales. Let's break down what this diagram represents. We start with a signal represented by coefficients C, J, K. The signal is passed through two filters, one with the coefficients H and low pass filter and another with the coefficient G and high pass filter. The output of these filters are downsampled by the factor of 2, represented by the below 2 operations. The downsampled outputs are then unsampled by the factor of 2, that up to 2, and passed through the original filter again. But the coefficient flipped and conjuncted indicated by the tilde. Finally, the results are combined to form the new coefficient at the next course level C, J plus 1, and approximation coefficient, and the D, J, K, the detail coefficients. As you can see, the diagram depicts a hierarchical structure involving multiple stages of a processing. G represents the low pass filter. This filter extracts the lower frequency components of a signal. H represents the high pass filter. This filter captures the high frequency detail of the filter. Down size 2 indicates a downsampling where every other sampling is discarded. C2 likely represents the coefficient at the coarser level of a decomposition, whereas the W could represent the original signal or input data. The diagram illustrates a multi-level decomposition process. At each level, the signal is split into two components, low frequency components, whereas it obtained by passing the signal through the low pass filter G followed by downsampling, and high frequency components obtained by passing the signal through the high pass filter H followed by downsampling. The low frequency component is then further decomposed in the subsequent level, while the high frequency component represents the detailed information at the specific level. Wavelet transforms can also be extended to 2 dimensions, provide powerful tools for image analysis and the application requiring multi-dimensional signal processing. As you can see on the slide, we are extending the wavelet concepts to 2 dimensions instead of dealing with a single variable. We now consider image represented by a function of 2 variables, x and y. The key idea is to separate the x and y dimension. We achieve this by multiplying one-dimensional wavelets. So wavelet types, we define the 3 types of 2D wavelets. One is vertical wavelets, focuses on vertical details; horizontal wavelets, which captures the horizontal details; diagonal wavelets, where it detects the diagonal features. The transform image is decomposed into 3 sub-images, each representing a different types of a detail. The equation represented on the slide provide a mathematical foundation of computing the 2D wavelet transforms. The detail signals WJK, KX, KY are calculated using a double summation involving the original image coefficients, CJ plus 1 into bracket 1 LX, LY, and the filter coefficient G, LX minus 2 KX, and H, LY minus 2 KY. Understanding the 2D wavelet transform involves decomposing an image into multiple frequency subbands, capturing a different spatial information. As shown in the image, the decomposition process yields 4 sub-images. LL, approximation coefficients represent the low frequency components of the image. LH, horizontal detail coefficients capturing horizontal edge and details. HL, vertical detail coefficients capturing the vertical edges and details, and HH, diagonal detail coefficients representing diagonal and point-like features. The 2D wavelet transform can be applied recursively to the LL sub-image, generating a multi-level decompositions. Each level provides a coarser representation of the image, while the detail coefficients at a different capture information at a different.
Good morning. Okay. Yes.
Let us illustrate.
Could you see my screen? Okay, fine. Yeah, sure. Yeah, it is audible.
Hello.
Sure. Yeah.
Hello, Professor Rao. Is it audible? Is it audible?
Yeah, it is audible.
Okay. So the next session is on discontinuous Galerkin methods for convention dominated fluid flows. It will be presented by Professor Srinivas Rao from Department of Mathematics and Computing from IIT Dharwad. Sir, you can start your presentation.
Yeah. So good morning to everyone. In fact, it's I think a little late. It's all right. So thank you very much for the organizers and the coordinators. Special thanks to Dr. Pavitra, who has taken up the leading role for arranging the sessions. So thank you for everyone for giving me this opportunity. Although I'm out of station, and but then once I committed and all, I decided that I should deliver a talk. So I will not be taking much time. Around for 30 minutes to 45 minutes I will be taking. So this is basically a discontinuous Galarkin method for convection-dominated flows. You see, there are many numerical methods for obtaining the solutions to the convection-dominated flows. Those who are working in the in the area of numerical methods, see that everybody using the what we call the finite difference method, finite element method, finite volume method, and discontinuous Galarkin methods. And in different versions of the methods, researchers have been using, but then every method has its own specialty. Like, for example, if you are talking about the implicit finite difference method, it could able to handle it could able to handle the nice problems with irregular geometries, arbitrary boundary conditions, things like that. But when it comes to the very, very complicated geometries, such as seismic waves or weather prediction or control systems, where the abrupt changes takes place, that is sudden changes. So the property could remain a fraction of seconds. For example, knowing very well the seismic waves, it remains only for very, very shortest time, maybe 10 seconds or 50 seconds, or at the most 1 or 2 minutes, not much. So how do you simulate those models in the realistic situations is the need of the day. So I would be presenting over here a small, the module of the discontinuous Galarkin methods, how it works for convection-dominated flows. See that the Galarkin methods, discontinuous Galarkin methods, the broad idea is the piecewise functions or shape functions which we try to include may not be continuous. If they are piecewise continuous, still I can able to adopt the discontinuous Galarkin method. That is the specialty of this discontinuous Galarkin method. These methods are completely discontinuous approximations. They produce mass matrices that are block diagonal. Any numerical method when you use it, you do obtain what we call a matrices. So finding out a solution to the matrices is also a challenging problem. All of you know very well, there are dense matrices, there are sparse matrices. These, once you get into the dense matrices, for obtaining the solution is very cumbersome, and many times it is not possible to have a approximate solution for dense matrices. So even if you make sparse matrices, still you would be getting into trouble. So it's a very litigation between the dense matrices and sparse matrices. Well, these methods are locally conservative, stable, and higher order accurate methods which can easily handle complex geometries. See that the idea, all of you know very well, there is what we call the HP refinement, that is the spacing between any two nodes would be lesser and lesser, and increase the degree of the polynomial. That is what is called HP refinement. When you have irregular geometries with hanging nodes that have polynomials of different degrees and different polynomials, it's a very, very tricky condition. And simply, reducing the step size and increasing the polynomial not only serve the purpose, but it will become a problem again. See that all of you know very well when you use this, the shape functions, linear shape functions, quadratic functions, cubic functions, higher order functions, you can able to handle the much more complex geometries, but the degrees of the approximations would actually increase. Okay, so therefore, those properties which render them ideal to be used with HP adopt to strategies not only have brought these methods into the mainstream of computational fluid dynamics, but have also prompted their application to a wide variety of problems. For example, second order elliptic problems. All of you knowing Navier-Stokes equations. So they are all elliptic in nature, but then finding out a solution is, it's a still evergreen problem, and many more approximations have come up, but still there is a lot of scope in order to handle those things. If you consider the simplest example, look at this d by dt of ut is ft ut, and t is 0 to t, mu 0 is mu 0. this is the initial value problem, and suppose that we want to compute an approximation UH to U on the interval 0 to t by using the what we call discriminative logical methods. I look for a function UH an interval and polynomial of degree at most k, which would require the integrals. So I do use the integrals instead of the differentials, the way which you do it in the finite method. So what I do is I will try to do the the what we call the simplest situation approximate solution of ordinary differential equations, and I will make it to this the integrals over the given domain. Well, you can also write it this as the link between the ODEs and PDEs. So you write it as U0 for Tn is equal to 0 otherwise, and this will become the most fascinating definition of the discrete Galerkin methods. So therefore, the enforcing of the ODE on each interval means of Galerkin weak formulation. That is what we mean by weak formulation. Is we require the first order the continuity, not necessarily that you should have the second order continuity. And also we introduce showing definition of the so-called numerical trace, which will take care of the many more stability conditions and convergence strategies. So the choice of the numerical trace is perhaps the most delicate and crucial aspect of the definition of the discrete Galerkin methods, and it can affect their consistency, stability, and even accuracy. It's not just that I am doing the first time the numerical procedures. There are many more numerical procedures that are available, but then what is the best accuracy I can be able to bring it, right? In general, we can say that what is the complexity of an algorithm which I am able to develop, right? The simplest choice we have made in quite natural for this case and gives rise to a very good method. However, there are many more choices. So therefore, the discrete Galerkin method is the what you call a revised version of the finite method, where actually the function need not be continuous throughout the interval, but if it is piecewise continuous, we could be able to apply the discrete Galerkin methods. So there are many more other properties that can be easily designed for any idea of accuracy in space and time complex. In fact, P version or spectral element of other type version can be designed. That is, you can have a different shape functions, spectral elements, higher orders, and things like that. It can easily handle adaptive strategies since refinement or unrefinement of the mesh can be achieved without taking into account of the continuity restrictions. This is the first advantage with respect to the discrete Galerkin methods. Well, there are many more properties like this. It has nice stability properties, local cell entropy inequality for the square entropy, and so on and so forth. And then you also do have what we call L2 stability, that is the Sobolev space functions. The matter is highly compact. The evolution of the information in any element depends only on the information of itself and its immediate neighbors, not the regardless of the accuracy. So that means it's a locally stable. So this is in contrast with higher order reconstruction. This compactness is responsible for the efficient parallel. So those who are doing the parallel computation, it can be easily done by using these methods. The model elliptic problem, that is what is called weak or variational formulation, the Galerkin finite method analysis and approximations, discrete Galerkin methods, mere compressibility, elasticity problems. You look at this simple example, minimization of energy. You see here, minimization of energy of times of integral LU square dx minus of the boundary. So it satisfies the weak problem in this way, what I wrote over here, and ultimately you will end up what we call minus del U is equal to F1 omega, that is on the interior, and U is equal to 0 on the boundary, where del is the Laplacian operator. Well, when you do use in the context of the bilinear shape functions or linear shape functions, you do end up with these expressions what I wrote over here, and more or less the symmetry property would help us in finding out the solution to those things. So when you look at this L2, that is Levasco space of square integral functions, and it satisfies all those properties, so therefore one could use the well-posenness also this. So for example, if it is cohesive property also, that is the bilinear form of A of AW should be greater than or equal to alpha times of norm of, that is 2 norm of 2h, and L is continuous. Therefore the model has unique solution in the sense of the log measures. So similarly, if you look at this here, a triangular property, and this is the square, and this is the trapezium, and a portion of hip replacement, physical object and finite element model. You see here, all of you knowing very well, there is a, total hip replacement, total knee replacement. How actually weight is falling on the biomechanics, they do calculate the stability of the stress and strain, how continuity of the bones takes place, so it gives you a very, very important in the medical sciences also. Well, look at the other piecewise polynomial approximations, 5i. So look at this finite element mesh. It looks like, the making into small finite element solution and finite element solution for the surface plots. So when you compare this, compare to the finite volume method, where you need to find out the outwards, the normal. So therefore, this method will exhibit that this will have a streamlines and other things. So look at this. The control volume approach, when you use this finite volume method, you do have a streamlines, right? So these streamlines are across the flow. So that each streamline will have its own shape. So you do have a specialized way of doing it. So similarly, when the f is differentiable in the Cartesian coordinates, also you do it, and in differential form you can do it. That is integral form you can do it. In the same fashion you can do divergence theorem. That is, how do you convert this square integral function into the divergence theorem and that. So both the conservation form and non-conservation form you can use it, and where you have the red letters which I wrote, it is the convection terms, where the convection is the dominating factor over the equations. So similarly we do it what we call mass conservation, momentum and energy conservation of these equations, and whereas this discontinuous methods you will have a very, very specialized property over here. You will see here there is a jump over here. So that means the function is continuous over this interval as well as this is interval, and there is a jump. So the jumps are actually finite number of jumps, so therefore one could able to apply the discontinuous methods. Where you do have a conformal mapping and discontinuous graphical mapping. You see here there is a shoot up over here, but on the broad side they do look like the same, but here the elements are very, very close to each other. Well, so look at this, the way bother with the discontinuous method. So not only just that, the closerness, and also you can be able to handle the hanging notes, that is abrupt variations, how you could be able to see those things and all. See, for example, when you increase the degrees of freedom, you see here, and displacement over the error for the case which we did it in the systemic waves and other predictions. Well, the derivation of the heat equation, when you commit here, heat balance equation, divergence of P is equal to S, and Fourier law of heat conduction, because solid you have it, so therefore you need to consider the Fourier law of heat conduction. Similarly, for the elastic bodies also you can use it, and if you use the Runge-Kutta method and ut plus fx is equal to 0, and Runge-Kutta method along with the discontinuous method, this is also one of the ways that how actually the researchers will be doing those things. So in general, semi-discrete discontinuous method, time discretization, cell entropy and all, then the error estimation, and so on and so forth we do it. Look at this, so the history of the discontinuous method is 1973, they used it for the steady-state linear scalar conservation problems, and 74 they used it for error estimations, and then they modified it, and in 1988 they did for the Runge-Kutta method for nonlinear conservation problems, and still there is changes over the years. Look at over here, it's Vj minus 1 by 2, and this is the Vj1 plus 2. So all of what I wanted to say, there is a finite discontinuity over here, so that we could be able to apply the methods. So not only just that, you also do have a Lipschitz condition for the stability of the differential equations, existence of makers, and also you need to do the lax flux condition for stability of the numerical schemes. So they are locally conservative, so therefore that's the advantage, no need to worry about the conservation of all those things. And you can also have what we call if you apply the Runge-Kutta method along with those schemes, you could be able to get this kind of elements. We did it small problem for the slider varying lubrication problem, discontinuous methods, and we could be able to get the nice solution for different one multi etc. in different parameters. We use the polynomial of degree k. So different degrees of polynomial we use it, and the current Fisher-Levy condition use this alpha is equal to maximum of f prime of w. Well, when it comes to the schemes and also the, what we call this, if you take further the multi-dimensional scalar equations, that is ut plus fux plus g of u is equal, so that when variables are x and y, so in that case, how it can be done it. So look at over here, transport equation, it would be like this, solid line exact solution dash line, and here also you see that for k equals 6, that is, when you use this, the linear, when you use the 6th degree, and k equals 6, you will have a solution very flat. So this is the transport equation, how it looks like. Similarly, for the transport surface plots, you can have this kind of pictures and complicated geometries and boundary conditions, one can do it, and entropy inequality also can be handled very nicely. And well, so when you have this, the inconsistent discontinuous method, there are many situations where actually the idea is that how you could able to apply the Galarkin methods, but there is inconsistency also does exist in the Galarkin methods. For example, if you take into ut is equal to xx and ux0 is equal to x. So therefore, the periodic boundary conditions, right? So we did it for the abrupt variations and hanging nodes, but when it comes to periodic boundary conditions, a straightforward generalization of the discontinuous Galarkin method from the conservation of law, that is ut plus f of u of x is equal to 0 to write in the stream function and replace f of u by minus ux, so that we could be able to get into that. You see here the way which I did it over here. But in any case, whether in a discrete case or whatever it is, there is what we call finite jump over here. So therefore, we could be able to apply these methods. So therefore, semi-discrete Galarkin method is simply like this, and this is the trace UH of x of j plus 1 by 2 is UH of x, j plus 1 by 2, one can do it. Therefore, for k is equal to 1 and t equal to 0.8 solid line, this is the exact line, and k is equal to, so when you go to the, that is linear and it is a quadratic. The solution of the inconsistent is a method for the heat equation on 0, 2 pi with u0x is equal to sin x, third order method that is used with the 160 mesh points. So the mesh is consistent to the heat equation to be very weakly unstable conditions. So in fact, 2005, when the Shu and Liu, they have done it based on the HJ equations and the hyperbolic conservation laws. All of you know very well, when you use the specific waves and all the equations will have acceleration and the consistent acceleration, so therefore they will fall in the category of hyperbolic equations. New ingredients also have come up, W is replaced by locally curl-free polynomials WH, and WH belongs to VH of k-1, and the mapping will be like this. Well, the missing contrast is in h is recovered either by requiring for each j, that is integral of it plus x times of ix by dx is equal to 0, this is the product, or by using update only a few elements, then after reaching the final term, you can have a method like this. So the accuracy is optimal for del phi and suboptimal for phi. Generally, it is necessary to consider the dependency of the components of W for accuracy and for steady state conditions. For nearly incompressibility discontinuous Galarkin method with the quadrilateral element is not straightforward. A remedy is select under integration of j lambda depending edge terms has been proposed, analyzed and shown to convert uniformly at the optimal rate. So therefore arbitrarily quadrilateral numerical experiments indicate behavior similar to that for rectangles. Analysis would be quite complex. So that means the method is, although it could be able to handle, but the analysis will become much more little bit complex over the years. So therefore, for those people who wants to do it, this kind of Galarkin method, and we did one problem over this, it is yet to be published, but there are many more articles. That is discontinuous Galarkin method for convection dominated flows, and there is a discontinuous Galarkin method for Navier-Stokes equations and hybrid grids, international conference on finite elements in flow taxon, and there is a normal discontinuous Galarkin methods analysis and algorithms application, Springer and all. So today I'm having some eye problem. Just now I came from the hospital, but then once I committed, I thought I should be doing it. So with this small talk, I will be able to close this discontinuous Galarkin methods. For beginners who wants to do it, and they can start with simply one-dimensional equations and they can go ahead with yeah. So now it is open for discussion. So I request that the audience please do. Yes, Sidhu. Yeah, Dr. Sidhu, please.
I am Professor Karnatak, sir.
Oh, that's nice, sir. Nice.
Yes, sir. Your talk was excellent. We are very happy, sir. Our audience are very much happy.
Yeah, Professor Girisha, some questions please.
I will call you back.
Hello. Hello, is it audible?
Yes, audible, please.
Sir, it is very nice lecture, really wonderful, and really those who are doing research, just started, sir, for them, really it is very useful. And also, I thought, I don't know whether it is right or wrong, so they can give the, connection between whatever you have given polynomial, sir, with those and also wavelet polynomials. I think so, I don't know. I have not tried, but seeing your, by listening your lecture, I thought like that. Is it possible, sir?
Sure.
Oh, thank you, sir. Very nice. So, nice to meet you.
Right, sir.
Okay. Thank you, sir.
Right.
Hello, sir.
Yeah, please.
Sir, in Taylor wavelet Galerkin method,
Yes.
so we are using legendary wavelet basis.
Yeah, legendary polynomials.
Legendary wavelet basis.
Legendary
Polynomial wavelet basis. Sir, here Professor Arya Kumara Chand is with us. Just he wanted to talk to. Yes, please. From IIT Chennai, sir. Arya Kumar Chand from IIT.
Oh, yeah,
IIT.
please.
Hello.
Yeah, please.
Yeah, so there these methods, whatever you told, whether you use stability analysis or anything.
Correct. Dr. Maria, please.
Whether you study stability part of this problem,
Again, please.
stability aspects,
Which aspects?
stability.
Stability aspects, yeah. See that when you are using these finite element methods, the stability and the consistency, they're all actually, very important properties. But when it comes to this descriptive hierarchy method, since the polynomials are piecewise, and the stability condition also need to be checked by using what you call Lax-Weierstrass theorem, and then some people are using Fourier's stability analysis also they are doing it. But we did this Cohen-Fisher-Levy condition for numerical scheme, and it is a stable.
So instead of these polynomials, can you use splines?
Yeah. So instead of polynomials, one could use spline functions also. Yes. But then again, you need to check the stability condition.
Okay, thank you.
Yeah.
Sir, it is over to the session chair, please.
Anybody have any questions from audience? Students, research scholars and students.
Yeah, I'm unable to come physically. Sorry for the online talk. I thought of coming, but then it is since semester started, and I was fed up with some hospital, and still I am not in the IIT Dharwad. So sorry for my inconvenience.
Sir, shortly we will invite you for offline also, sir. You be ready.
Sure. Next time and all, I will make it in physical presence.
Yes.
100%
Thank you.
sure.
Okay, sir. Thanks a lot for giving a wonderful talk.
Yes. Thanks for your coordinator and chairman, all the members who have done it excellently, and they are monitoring from the day one onwards. Although I am going here and there, I could able to hear their response. Thank you very much for everyone.
Thank you, sir. Now, the next speaker is Dr. B.J. Girisha. He is currently working as a professor at Department of Mathematics in Coimbatore University. So he has 24 years of experience. His research area is fluid mechanics. He has a very great research achievements. He has published more than 460 research articles. And he has received 2 awards. He received Sir C.V. Raman Award by Government of India in 2015, and he also received C.V. Raman Young Scientist Award from Government of Karnataka in 2022. His H index is a very remarkable H index. He has 62, and he has 12,000 plus citations. A very wonderful biodata he have. Now I request Dr. BJ Girisha to take over to deliver the talk.
Thank you very much, sir, for your introduction. A very good morning to you all. Respected professors from different institutions and dear PhD students and MSc students and all others. Today, so who will present? Today I am going to deliver the lectures on what are the importance of dimension analysis and also similarity transformations. I think many of you are doing research in fluid mechanics, especially on stretching sheet problems as well as microchannels and different kinds of fluid mechanics problems. Wherever you go, whatever the problems in fluid mechanics, there you have to solve Navier-Stokes equation as well as energy equation. As you know, Navier-Stokes equation is a highly nonlinear partial differential equation. Till date, it's an open problem. It's a challenge to solve analytically. But we know different kinds of method to solve the problem, starting from Poisson-Lee as well as Cotte. So they have put restrictions on Navier-Stokes equation and they reduce the equation to simple form. Then they start to find the solution and then they analyze the physics behind the problem. So these are the methods. This is the way what we are following in, especially those who are working in the field of fluid mechanics, especially on stretching sheet problems as well as microchannel problems, in fin problems, whatever the problems. So their fluid flow occurs. Yeah. Pavitra. Is it? Okay, thank you. All right. So as you know, here finding the solution to Navier-Stokes equation as well as, a coupled equation like Navier-Stokes equation and energy equation, it's a difficult task because Navier-Stokes equation in nonlinear form. Before going to start my lecture, I want to remember one person, great personality. He is behind us to do something new in the research field. That is astrophantaquataresis. I think you may have heard of you, those who are working in the field of fluid mechanics. He is a mathematician. He working with the same field, means fluid mechanics, in stretching sheet problem as well as microchannel, all the problems. He has published more than 1,000 papers. How his papers, number of pages around only 1 or 2 pages. Simply by writing 1 or 2 pages, he is going to publish the papers, and there are more than 1,000 papers. How he is going to work? He is not going to formulate any problem. He is not going to solve any problem. He is not going to find, write any program in any language. just by finding the mistakes, those who are already published, and point outing the mistakes, he is going to publish the papers by writing 2 or 3 line comment on the paper. Like one day, I received one mail from editor. So Girisha, he wrote like some comments on your paper. Whatever the equations you have taken are wrong according to Astero. So then I afraid of him because I heard his name earlier because he wrote many comments on many authors, but he has not touched me. But one day I received mail, by that time really I am afraid. So he come to me also like Shani. So what to do next? So I saw the comments and for 15 days I ignored the mail. Once again the editor mailed me, no Girisha, you have to give the comment to this paper, to his comments, otherwise the people, think in different way about you. Then so I sat with my student, Dr. Prasanna Kumara, now he is working in Dharwad University, and one more student, Rudraswamy, now he is in Hubli only, and myself, we sat together in my home itself by around night 10 o'clock. We started work on it, and we find that so there will be no mistake with us, and he mistaken. So he has, missing while calculating the dimensions. Then we wrote the, report against his comments, and that paper was published again in 2 pages in the same journal. So on same formulation, earlier I published the paper in the Springer journal, and Astero commented on my paper and he published the paper in the same journal. Again further for his comments, I wrote the comments and again I published the same paper in the same journal. In the similar manner, so I wrote the comments in arrogantly because he has not observed the equations properly. So that paper was on dusty fluid. He didn't know what is K. So because of that reason, so he got misunderstanding with the, governing equations, and he wrote. Similarly, I saw, usually who are working with stretching sheet problems and microchannel problems, Reynolds number, Nusselt number, Prandtl number, Eckert number, like that we are going to get different kinds of non-dimensional numbers. But usually, in earlier problems, they use them as only Reynolds number, Eckert number, Prandtl number, like that only. But nowadays, the people start to use the names as local Reynolds number, local Nusselt number, local Prandtl number, like that. Why? Why they are calling? Because, so after applying similarity transformations to the equations, the partial differential equations reduce to ordinary differential equations. When they reduce to ordinary differential equations, you are going to get the non-dimensional numbers. But in those non-dimensional numbers, the local variables like x, whichever the variables, so whatever your formulation, there may be 2 variables, or there may be 3, or maybe there may be 4. So if you are going to take 2-dimensional flow, then there will be 2 variables. If you are considering unsteady, then 3. So 3-dimensional with unsteady, there will be 4. By applying similarity transformations, sure, so whoever call them as local Reynolds number, local Nusselt number, like that. So in those numbers, there will be a local variable like, there will be x remains or y remains in those. They are going to hide that variable in those Reynolds number. And sure, they are not non-dimensional one, but our claim is they are non-dimensional. Then sure, obviously, our claim is wrong. Simply, Astero, observe that non-dimensional numbers. If you have, so local variable in that number, and sure there will be, they are not non-dimensional. Just by writing whatever your claim, Reynolds number is non-dimensional, it is wrong. Hence, your entire result is wrong. That's why, so your claim is wrong. Like that, by writing 2 or 3 lines, so he used to publish the paper. Then we so thinking how to avoid these local variables, including myself. Thousands of papers were published with the same mistakes. Till date you can find in the literature. Till date you can find. So stalwarts, even stalwarts, those who are worked in fluid mechanics like Sakya Das, Sakya Das also did the same mistake, and they have published the paper. So with local Reynolds number, local Prandtl number, like that means local variable remains, but it should not. After the comments of Astro, we realized that they should not available in the these non-dimensional numbers. Then what to do? How to correct these things? How to avoid these mistakes in research? Most of us doing the same mistakes, including me. I did the same mistakes in my earlier research work. What we are going to do in our research usually, we are going to take some stalwart problems like Sakya this problem or any Aziz. So many authors. So we are going to take some problem. Whatever the effect they left, we are going to add some new effects in the formulation, and we are going to solve the problem. But the thing you should remember, to solve PDE, we are going to apply similarity transformations. After applying similarity transformations, our PDE going to reduce it into ODE. Once it reduced to ODE, we are going to apply different kinds of methods, like it may be Runge-Kutta method, or finite element method, or finite volume method, whatever the methods, that doesn't matter. Here the thing, I took the Sakya this problem, I added some parameters to the, basic equations, like I'm going to do new formulation to my problem. What I did, I took the same similarity transformation, whatever the transformation used by Sakya this, and I'm going to reduce. Then finally, sure, there will be a local variable in the reduced equation. It means for your own problem, you have to derive your own similarity transformation, then only it is possible to avoid local variables in the non-dimensional numbers, and that is the appropriate way. That is the appropriate way to solve. Then how to reduce and how to derive these equations is very important. So I am going to show you some problems. Whatever I am going to show you in the next slides, my paper is also included. I have not included the author's name. Okay, just I took the problem and whatever the formulation and whatever the similarity transformation they used in their paper, and those papers are published in Q1 journals, not in ordinary journals. They are all published in Q1 journals. So go to next, please. Next. See, go back. See this problem. It is published by some XYZ. I don't know the author. Now, so it is published in International Journal of Mechanical and Material Engineering in 2018, recently. His formulation, so whatever he took, it is the, two-dimensional flow. You mean X and Y are the independent variables. Okay. So go to next. So see there. These are the similarity transformation taken by the author. These are the similarity transformations taken by the author. So similarity transformation means here we are reducing the partial differential equation to ordinary differential equation. Means, so partial differential equation means there will be two or more independent variables. You are reducing PDE to ODE means in ODE there will be only one independent variable. It means your similarity variable, that is so-called eta in our papers, eta must involve whatever the independent variables in the partial differential equation. Like in this partial differential equation there are two variables, x and y. Then your eta should involve both the variables, both x and y. See, here the author considered the similarity variable. See there, eta is equal to some constant into y. eta is equal to some constant into y. Then forget about the constant, it is nothing but eta is equal to y. Then how it becomes transformation? How it becomes similarity variable? Your similarity variable should involve all the variables whatever appear in the partial differential equation. But here simply eta is equal to some constant into y means just you are replacing eta instead of y. That's why, so whatever the formulation you considered is right, but whatever the similarity transformation are wrong. So that's why your non-dimensional numbers includes local variable, like it may include x or it may include y or it may include t. Okay, that's why you have to avoid these things. So in the next step we can see how to avoid and how to derive our own similarity transformation. But here you see, so these similarity transformations are wrong. It is enough for Astero. It is enough. You used to write your paper is wrong because eta is wrong. That's itself, you will get one paper. Okay, go to the next. And this is the paper published by another author, another XYZ. So these are the formulations, see there. So variables are R and S. Small r and small s are the variables in the governing equation. Go to next. See there, your eta includes only R. There is no S, and it is published in very reputed journal, and the author is also very reputed person. Okay, next. In title 3, so here also you can see the basic equations. There will be two variables. Next, so your eta contains only y. Strangely, you see next, and sure you will afraid. Go to the next. See there, x and y are the variables. Next, so only y. Next, please. Here also x and y are the variables. Here eta, see, y. There at least constant was there. Here eta is equal to y. How it becomes similarity transformation? Simply by replacing y by eta, you are claiming, means I am claiming, because I am also one of the author, did the same mistake. Okay, I am claiming it is the similarity transformation. That's why, so till date, the authors are doing the same mistakes. That's why I'm going to give this lecture. So my intention is to say, avoid these mistakes. Once we know they are mistakes, so now we should try to avoid these mistakes in coming research, okay, in coming papers. So in this context, so I gave this work to two of my students, one Pavitra and one Sushma. Yesterday they have presented their paper, so in the presentation. So they are doing the research work based on this. Simply they are deriving new similarity transformations to these problems, whatever already published, but the papers are wrong. How do you claim they are wrong? I will show you in the next slides. Okay, so they are deriving own similarity transformation for their own problems, and they are so finding the solution, and no local variable remain any non-dimensional variables. I mean non-dimensional numbers like in Prandtl number, Eckert number, strain friction coefficient, everywhere. So wherever you see, so you can't find any local variable. That's the thing those two are doing. So earlier they are afraid because I should refer some XYZ. So Kumbi Narsaya did same mistake. So that's why we are derived the new similarity transformation. Kumbi Narsaya, whatever the similarity transformation taken, they are wrong, and they are the real similarity transformation. Like that we wrote the paper and we sent for the publication. Actually the editor should send to Kumbi Narsaya only, because we mentioned his name. Kumbi Narsaya did the same mistake. Kumbi Narsaya got, angry with us and simply wrote, this paper is rejected. Really, earlier, so when we start, all the papers coming back within a week. So you're, rejected with no reasons. Then those two, especially girls, they started to weep. They started crying. They literally crying. Sir, all papers are coming back. Sure, our PhD will not completed. So what to do? So then I told them, no, don't worry. This is the truth. What we are doing is the truth. So one or other day, the people should accept it. Because this is the truth, So they should accept it. Simply you work on it and send the paper for publication. Okay, they listen to me and they are confident with me. So sir will anyhow award the PhD with so he is there, why should you worry? So like that they start to work and they start to publish the papers. Now we have published very good papers in very good journals and the same authors have accepted their mistakes. So that's the thing we should appreciate, because next, my sincere suggestion is next, while to start your research, please don't go blindly with similarity transformation with earlier paper. You have to derive your own similarity transformation for your own formulation. Then only that paper will become very good paper and it will publish in very good journal. Okay. So in the next slides, I'm going to show how we are going to derive our own similarity transformations. Right. So next, one more mistake. Next, go next. Skip this. Same, all our mistakes did by the authors. Go back. Next. Next. Okay, down, please. Next one. Okay. Look here. You may see the papers like non-linear stretching sheet problems. You may have heard about this, and I think some of you may publish the papers on non-linear stretching sheet problems. Non-linear stretching sheet problems means your capital U must be A into x to the power n. For linear, A into x. A is the stretching rate and x is the length. Okay. Usually we are going to take like this. A into x for linear problem. For non-linear problem, non-linear stretching, we are going to consider it as A into x to the power n. Means n must be not equals to 1. U, what is U, capital U? U is velocity. What is the dimension of velocity? Meter per second. Is equal to A into x. A is stretching rate, means per second. X is length. X length, represents length. That's why meter per second. X is length, meter. Rate is per second. That's why meter per second. Left hand side, right hand side. So balanced. That's why U is equal to A into x is appropriate. No problem. There will be no problem. Come to non-linear problem. Non-linear means n must be not equals to 1. If n is not equals to 1, your LHS is, your LHS means your climb. Your climb is velocity, that is meter per second. But come to right hand side, n is not equals to 1. Okay. A is stretching rate per second is there, but x power is there. X power 1 by 2, then meter power 1 by 2 per second. Is it the dimension for velocity? For n not equals to 1, it doesn't becomes dimension for the velocity. It is not balanced. Then how you are going to climb non-linear stretching? And this is the mistake, and this was the mistake done by many people, including myself. I am not the person, so I am also did the same mistake in earlier papers. So this is the mistake, right? So we are going to climb x is, U is equal to some A into x power 2 or x power 3 or x power 1 by 2, then it becomes non-linear, but the dimension is not balanced, means my climb is wrong. Once again, you have to take into consideration. So, by take into consideration means you should involve this also to derive your similarity transformation for your problem. Then next question is how to derive these, how to derive similarity transformation, so for our own problem. So go back, earlier slides. First slide. Okay, next. See, so I have taken simple example, heat equation. So ut is equal to some uxx. ut is equal to some uxx, simple example, right? So, and with corresponding boundary conditions as well as initial conditions. So, there are three kinds of methods to derive, one translation, dilation and other one. So, you can apply three methods to derive similarity transformation. Here we have introduced dilation transformation, and I took z is equal, okay, Pavitra, let it be. Z is equal to epsilon power a into x, and s is equal to epsilon power b into t, and u is transferred to v. So means original equation involves the variables t and x, independent variables, and u is the dependent variable. I took the transformation so as x as z with some constant, and t as s with some constant, and u as v with some constant. So then how to derive our own transformations? These are the considerations, and by taking these and by simplifying, and by taking the derivative, first derivative with respect to t and with respect to second derivative with respect to x, the equation, the derivatives will appear with respect to s. T, instead of t there will be s, and instead of x there will be z. Instead of x there will be z. You are going to get the equations. Next. So equations are disappearing. Why? PDF. Okay. Go to PDF. Go to PDF. Stop sharing that one. Mail. Okay. Make it full screen. Make it full screen. Close PPT and open PDF. Yeah. First one. Okay, see there, go back, one slide back. By finding the derivatives, whatever are required for the original equation, so we find the derivatives and substituting those derivatives in the original equation, then we got the relation between the constants, epsilon power a, epsilon power b, epsilon power c, like that. Then we are going to get the relation between A, B, C. Then using those relations, you have to find the values for A, B and C. Here you got, so B is equal to 2A, or A is equal to 1 by 2 into B. So then by taking these transformation, go next. And by substituting, there you can see u is equal to t power c by b into f of eta or y of eta, whatever the variable, and eta, your eta becomes x by t power a by b. You know a is equal to 2b, substituting your eta will become x by square root of t. X by square root of t, then eta contains both the variables which are appear in the original equation. Then by substituting that eta and this y in the original equation, your differential equation reduces to ordinary differential equation involving only one variable, because ODE means there will be only one variable. It should not involve any x or t, right? So this is the equation. So go to next. So you can see this is the equation. Here also you have to remove constants by using your initial conditions as well as boundary conditions. You have to substitute this transformation to your initial conditions as well as boundary conditions also. By substituting there, again you are going to get the relations, because you know the relation between A and B, but here you can see C and A are there. Then you have to find the relation between A and C, and you have to remove those A and C. Next, by substituting here, you are going to get the final equation. You can see at the last equation 5 number. So that is the differential equation involving only one independent variable, means ordinary differential equation. It never contains any local variables. So this is the method. I mean, this is the way to derive the similarity transformation to your own differential equations. So for MHD problems, you are going to face some problems. I mean, a difficulty while deriving, but even though it may took 1 or 2 days. So they used to take 1 or 2 days to derive their own similarity transformation. For first day, sure you are going to get boring, and sure you are going to get irritation. So it is not a problem. I am not going to give somehow. So okay, somehow I can manage. It is not possible, like that you are going to feel. But so you are steady, and you are dedicated, sure you will get your own similarity transformations. Right? Next. So this is another problem, and same procedure, whatever the procedure followed in the previous problem. So next, you should remember, you have to apply this transformation not only to the equation, you have to apply this but also to, so whatever the initial conditions you have considered, whatever the boundary condition you have considered, then only it is possible to remove the arbitrary constants A, B and C, and eta purely in terms of the variables, okay, and U purely in terms of new variable eta, okay. So see here, so go back, see here, that is the, I mean, last equation. While doing formulation in fluid mechanics, there will be lot of difference in the equation. Then how you are going to consider the old similarity transformation for your newly formulated problem? That's why that is wrong, and because of that reason only we are going to get the local variables in non-dimensional numbers. Okay. Next, see this Burger's problem. Here also we derived eta. Next, what is eta? So go back please. So eta is equal to x by t to the power m plus 1. Eta is equal to t to the power 1 divided by, x divided by t to the power n plus 1. Simple change. I mean, by this you mean that for each partial differential equation, there will be a unique similarity transformation. Means, so a single similarity transformation will not work for all problems. Means, for each problem, you have to derive your own similarity transformation. Okay? By this I mean, so each differential equation have unique similarity transformation. Okay? Next, similarly I derived for this one. This is, so what you call wave equation. For the wave equation, eta is different. So eta is equal to, so next. So derived equation, so it is independent of this. Next please, run it. Now run it. Okay, go back. Okay, so here we took one problem, so new problem, so who were published already, but they have taken wrong similarity transformation. For the same formulation, we derived our own similarity transformation. See there, eta is equal to y divided by x to the power 1 by 3 into so and so. With this similarity transformation, we derived the equations. Next. we derived the equations and we solved the equation using XY method. Okay, it may be Runge-Kutta, or it may be shooting based, or it may be finite element, whatever the method you can use. So by using that method, we find the solution. See the, difference in the results. Earlier results, 1.23 so and so. For eta is equal to 0. See there, so 0.75 means you can find large difference. Then how do you claim your results are wrong, right, and their results are wrong? It means we have to give the clarification. Okay, so in the next slide. So same thing, here also I did the same thing. Next. So here, see here, previous results, okay, present results with perfect similarity transformation for some, limiting cases. For some limiting cases, some XYZ has published the paper with appropriate similarity transformations, and we derived our own similarity transformations and find the results and compare with his results for some limiting cases. Then you can see the, accuracy between the perfectness. There means the results, whatever they published, are wrong. That's why here my suggestion is, next, see here also, we used to do the mistakes. See there, graphs once, so here they are in decreasing manner. At lower side you can see the increasing manner. To show the property of the fluid, it should be same throughout the graph, throughout the area. Okay, but once you can see decreasing manner, but once you can see increasing manner. We need decreasing manner, that's why we consider that graph. Why not the bottom one? Why not the bottom one? Is it? So it means the graph, pattern of the graph should be same throughout the. Hello, please mute your mobile. Okay. Hello, mute mobile. Hello. Hello. Okay, ಬಿಡಿ ಮ್ಯೂಟ್ ಮಾಡಿದ್ದಾರೆ. ಮ್ಯೂಟ್ ಆಲ್ ಮಾಡ್ಬಿಡಿ, ಮ್ಯೂಟ್ ಆಲ್ ಮಾಡಿ, ಆಮೇಲೆ ಓಪನ್ ಮಾಡಿ. ನಂದ ಆಡಿಬಲ್ ಅಲ್ಲ ಸರ್, ಕೇಳಿಸುತ್ತೆ ಇವರಿಗೆ. ಈಗ ಆಗಿರ್ಬೇಕು. ಓಕೆ ಓಕೆ ಓಕೆ. See that graph? Delta 5. ಓಕೆ, ಅದನ್ನೇ ಮಾಡಪ್ಪ, ಕೊನೆಗೆ ಹೋಗು, ಅದ್ರಾಗೆ ತೊಂದರೆ ಇಲ್ಲ, ಅದರಲ್ಲಿ ಈಕ್ವೇಷನ್ಸ್ ಏನಿಲ್ಲ, ಅದರಲ್ಲಿ ಗ್ರಾಫ್ ತೋರಿಸ್ಲಿಕ್ಕೆ. ಓಕೆ, see there, upper part of the graph in the right hand side, okay, the nature is different, and bottom of the graph, lower side of the graph, the nature is different. So in upper side it is in decreasing manner, but whereas in case of lower side it is in increasing manner. We know the effect of different parameters on the fluid flow. Suppose Reynolds number, then the velocity should decrease. So where it is decreased, there we are going to put the arrow. Then we are going to claim our result showing that so velocity is decreasing as Reynolds number increasing. How? So I am going to take the other part of the graph. Then sure it will be wrong, Means without appropriate similarity transformations, you are going to get the graphs like this only. Okay, next. So conclusion is, and it's also a suggestion or request, whatever, so how you are going to take it, please derive your own similarity transformation for your own problem. Okay? So, in this occasion, I would like to thank organizers, Professor Shiral Shetty, Professor Ramane, Professor Patil, Professor Madams, to all others, okay, and research scholars and MSc students of this university for this opportunity. Thank you, Nandal. If you have any questions, feel free to ask me, okay?
In the starting part it is decreasing and the next lower part it is increasing. In most of the papers they have said it as overshoot and undershoot. And that concept is it wrong or?
No. So you derive for your same problem your similarity transformation and plot the graph, then tell me.
Okay, sir. And in other
Means
cases,
it is wrong. You should not get like this.
in all the cases we should not be getting like this.
Yeah. So there will be only one nature. In melting surface only it differs. In melting surface only it differs. In all other cases, the nature should be same.
Okay, sir. And one more question. If the graph is like for beta equal to 1, it is first graph you obtain, and for beta equal to 2, the second one, it is decreasing, and for beta equal to 3, if suppose it is coming above the beta equal to 1.
No. It is not possible. Because the nature, so like beta may be any non-dimensional number, and against that variable, against that number, if the velocity or temperature is decreasing means it should decrease for all values. It should increase for all values.
That
If
means
it is
there must not be oscillations also.
No. There will be no oscillation.
Okay, sir. Thank you, sir.
Sir, good afternoon. So can we use same for 3 independent variables? For example,
100%. 3 or maybe 4. So 3-dimensional with unsteady problem. So there will be, eta should contain 4 variables, x, y, z and t. So then only your problem is right. Otherwise, whatever the transformation you have considered is wrong. That is a simple way to check.
and can we generalize it also for
No.
number of variables like?
Yeah, 100%. Whatever the variables appear in the governing equation should appear in eta. Okay?
Thank you, sir.
Thank you, sir. Thank you for your presentation. I think I'm not asking the question, I think claiming on her question, she is asking the question with respect to boundary layer theory, not with respect to the stretching sheet.
Stretching sheet, boundary layer theory, basic equations.
I think in boundary layer theory, we have the oscillations if beta is negative, that is de-accelerated flows.
Beta negative means you are going to take either increasing values or decreasing values.
No, adverse pressure gradient, we have oscillations. Because in our paper, we have an exact solution, even not numericals.
Okay, fine.
So if you have a closed form solution, of course, we have
100% right.
100%
There
right.
will be no question of
Yes.
similarity
So
transformation.
because we have oscillations in exact, so that means I hope so. Madam is.
So oscillation means the effect, your assumption, whatever the assumptions you are going to take is considered.
Yes.
Whatever the assumptions you are going to take is considered, like pressure gradient, constant pressure gradient, linearly varying pressure gradient, or oscillating pressure gradient. In those cases, sure there will be variation.
I hope, in my opinion, I think stretching sheet does not have that nature because of
No. So
problem.
wherever, it may be stretching sheet problem or it may be boundary layer problem.
No, because of in boundary layer that beta has related to the angular wedge.
No.
I think-
So in stretching sheet means boundary layer theory or stretching sheet. In boundary layer theory, you are going to consider only the lower surface and upper surface as ambient.
Yes.
Okay?
Sir.
In stretching sheet also, you are going to consider ambient, then both are the same. If you are going to take rectangular channel between the plates, then
Anything,
only,
anything. Yes,
so
sir.
it differs.
Yes.
Okay? Is there any? Thank you. Thank you very much once again.
I thank Professor B.J. Girish sir for a wonderful talk. So with this session will end. Thank you.
University, Shankarghatta, Shivamogga. Sir has 24 years of teaching experience and the research areas are fluid mechanics. Sir has published more than 460 research articles and H index is 62 and Sir has more than 12,000 citations. Sir has awarded Sir C.V. Raman by Government of India 2015 and C.V. Raman Young Scientist Award in 2022. Sir has also visited USA for his postdoc. With this brief introduction, I request Dr. B.J. Girisha sir to chair this session.
Thank you very much. So it's give me an immense pleasure to introduce Dr. Kumbi Narsaya. Actually, he was working for the Karnatak University earlier, I think for the 4 years or 5 years, 6 years. Then he moved towards Bangalore University. Now he is working in Bangalore University and he has 10 years of teaching experience and he is working with wavelet analysis. His field of specialization. With this field, with this early age, 10 years of experience, he has published 102 papers, 102 publications in very reputed journals like Springer, Elsevier, and Q1 and Q2 journals, not in any below journals. And the great thing, his name, he is recognized as one of the scientists in the world by Stanford University last year. Top 2% of scientists in the world. So that was ranked by Stanford University in the last year. And he is working with, now present, he has 3 funding projects, national, different funding agencies like UGC and the DST now. So currently ongoing projects, so 3 research projects. With this brief introduction, I would like to welcome Professor Kumbi Narsaya to deliver the lecture. Please.
Good afternoon to everyone. So, First of all, I would like to thank this international organizing committee members for giving me this opportunity to deliver concept where I'm working actually. So actually, since from yesterday you have heard the concept called wavelet, right? If you heard the concept of wavelet, definitely in mind you will get it. It is one of the branch in the applied mathematics, right? So everyone just seeing the wavelet as a applied mathematics, that means they are using the wavelet to solve some of the ODE, PD, some of the fractional, so etc. But now, if you wanna apply this wavelet into get a solution of some differential equations, it must be overcome, it must be across some of the beautiful properties of pure mathematics. So now I am going to say that the why I am saying I am observing this wavelet through the wind of pure mathematics. Actually it is a basic, the entire body is pure mathematics. For the pure mathematics concept, just we are wearing different the suits suitable for our differential equations. But how? That means in this but here I am going to say that the how to create the wavelets, how the wavelets has been generated using the sum of the concept of real analysis, linear algebra and function analysis, because these are the major three concepts. Without this, no one will never understand what you mean by the wavelet. If you are thorough in these three concepts, definitely you will play with the wavelets in different way, and you can also generate your own wavelets. So what are those properties? And it certainly obeys some of the properties, and what those properties will does with your wavelets, so-called wavelet. So here, so next I am going to construct the way of construction of orthonormal basis, which is going to be generate the wavelet, and after that I have created one of the numerical technique by using the sum of the continuous wavelet, and then one small example for the application, because without application you won't accept, right? So that's why I will give one example how it works, where it works, when we wanna let it to work. Okay. So honestly speaking, so according to me, the wavelet is a pure mathematics. So pure mathematics, however, it is only few years existence of theory. It has a tremendous application in seismography, signal analysis, image processing, everything. But now I am going to talk about only strictly on pure mathematics basis and application of towards a differential equation. So on general, just forget about the what is wavelet. For in general definition, if I want to define a wavelet means, that definition says it is nothing but a functions. The wavelets are functions, and that satisfies certain requirement of waving above and below the x-axis. That means here I am not choosing entire wave defined in the entire real number system. Now just I am choosing only where it is going to be localized with minimum the support. I am going to choose these functions, and it is going to be localized, and we know how the the wavelet theory we are considering. Many of them already taught you from since yesterday. So that means the 4-year series work on the periodic the functions, right? To overcome, they used linear transformation, and for the linear transformation, so we are going to use this wavelet theory, because it is going to be defined in the entire domain by using the translation and dilation parameters. So next, and while if you see the in application level, many of them used either discrete, continuous, smooth, or wavelets with complex functions, so etc. So here I will first beginning I will say how the discrete wavelets generation using the concrete Hilbert space, and then I will take one compact, this continuously continuous wavelet, and then its application. So now in the introduction part, if now we are going to dealing with one space. That space is called Hilbert space. That means in the pure mathematics, any function, if I chosen, I will be preferred in the Hilbert space. And those functions obeys some certain, I call this is going to be the special functions which has been, multiplied by the, dilation and dilation and translation parameter. Next. Now first one, whatever the equation I have given. What this equation says? So in the Hilbert space, L2R means Hilbert space. If I choose one orthonormal basis, let it be, I consider one vector, sequence of vectors, let's say Ek. This vectors has been defined in your Hilbert space. But the one of the famous theorem, that means characterization of orthogonal theorem, it says, if any function belongs to your Hilbert space, obviously we can express this into linear combination, right? So with using the orthonormal basis. So just, I have chosen one function, let it be from the Hilbert space, and I have expressed in terms of the linear combination. So with that Ck, which is going to be K is the index set, which is infinite. Remember, infinite. Have you understood that equation, representation? Now I need to calculate that Ck. On practically, no need to be just, don't think in concrete definition way. Just in practical, if I use the f is a e power x, just it is a simple function, e power x into log x. This is my function, belongs to your Hilbert space. Now I want to express into linear combination of infinite basis. Linear combination of infinite basis. Now how is it possible to express? Enter, if you give 1 year time, even 1 year time is also not enough to find each and every values of Ck, right? So that's why, while defining the convergence of series, we say we consider only nth partial sum because of that reason. So nth partial, here also we are going to choosing the nth partial sum. That means those nth partial sum are going to be dominated by the coefficients Ck. So they are going to be dominating. So that's why we are saying the nth partial sum, whatever the value we get, that will be same as the summing of the entire infinite terms, right? Now, who is there to say what are the dominant coefficients, right? That is a topic. That is in which way I can choose the dominating coefficients. Yes? So many of you across this concept, yes or no? So, but how I can take the dominated coefficients? That will do by wavelet. The wavelet give the dominated coefficients. So how, after some of the concept, after you will identify how the wavelet will give the dominated coefficients. Next. Here, mathematically, if we say the wavelet, this is the definition of wavelet. All of we know this is the definition of wavelet. And if it satisfies whatever the function psi j comma k, a function of x, if they forms an orthonormal basis, then obviously we can say the psi will be wavelet, belongs to your Hilbert space. This is a routine definition we are using. And for my simplification, for my convenient, I am choosing, let it be dj is a which is a dilation parameter, and tk is a translation parameter. But here this definition says orthonormal basis, right? Orthonormal. Now I need to check. I am very much interested to check how it is going to be satisfied this condition, orthonormality. So afterwards you will definitely understand why I am more emphasizing on the orthonormal basis. They are the beautiful property. Next. So here I am going to check. This is the definition of Haar wavelet. So in the same Haar wavelet I am going to use orthogonality property, orthonormal property. Next. Here, let it be choose. I have told, I am very much interested to check whether it is going to be orthonormalized or not. I have chosen two functions from the orthonormal basis. That is the basis. So because I have considered the Hilbert space, so that's why I have chosen inner product. So inner product of these two functions is equal to, so previous notions, dilation and translation, I have used it. And the D, dilation parameter is unitary, so that's why the unitary apply of the unitary concept, then I will get inner product of tk psi, tk psi. Again, I use this because it is nothing but a wavelet function. So let's say integration minus infinity to infinity. So as usual, only translation parameter. So this is exactly equal to lambda k comma k prime. So if k and k prime are same, then it is 1. If it is not same, then it is 0, right? Orthonormal property. Now orthogonality I am checking. Now I fix, previously I have fixed the dilation parameter. Now I vary the j. The j prime is not equal to j. Obviously one must be either greater or less. So as without loss of generator, I can choose the j power k greater than j. Using the same inner product space, again I use the unitary concept in the Hilbert space. Then finally we get back. Finally we get the inner product will be the last one. This will be the inner product by using the properties of the Hilbert space. Now this I am going to say the support of this, that is the inner product of this. Next. So here the psi has a support 0 to 1 because R were defined. And now the newly obtained function, let's say t minus kj, 2 power j minus j prime plus k into psi, its support is this. That means support is this. And then after taking the dilation, and this support will be this. And finally after simplifying, I will say this. Okay? I am not more emphasizing on simplification. Finally, if you want, you can check it. The same thing will come. Next. And now the length will be 2 power j prime minus j. That means for any values of j prime and j, so value, the length of I will be 2, 4, 8 and so on. But previously psi length will be 1, right? The previous sign length will be 1. So therefore it is contained in the interval of whatever the function we have defined, which is also constant in the given support. So that means as usual, if I take into inner product, then definitely it is going to be 0. So why it is going to be 0? This is an example. So previously the psi will be supported by the 0 to 1, and now the new function, whatever the inner product I have chosen, that will be defined, the length will be 2, 4, so on. So that's why if I consider 2, definitely the integration will be 0. So therefore, what I done here, just I have taken is just function. I have shown that they are the orthonormal base, orthonormal functions, right? Yes or no? If I show simple functions to a orthonormal, how much work I have did? Is this process required? Yes, we can skip it out, these process. Okay, if I just choose a simple wavelet, hard wavelet, so it is easily we have overcome this relation. If I choose continuous wavelet, it is not similar to your hard wavelet. It is little bit behind, right? Then if you check, so those type of the functions, then of course we can check, but the length will be more, right? So that's why the new concept I am going to use, that is nothing but the multi-resolution analysis. Next. So here in the 1986, the Malat and Mayer introduced the multi-resolution analysis as a general tool to construct the wavelet basis and the orthonormal basis. Move to the definition. This is the definition. Just simply we say the multi-resolution analysis says these are conditions, right? Every book, you see the book, they definitely identify, oh, these are the definitions of your multi-resolutions. Okay. What these each and every condition says? We have not defined simply, right? Each and every condition, each and every property has its own importance. So first one says, it is going to be nested. So that means if you chosen the V0, if V0 is a space, I am just all speaking about the spaces, so which are going to be subset of your Hilbert space. V0 is a space, then you take a one dilation, then obviously it will going to be subset of V1. The D of V0 is going to be V1. So the first property says it is going to be nested, and second one says if you take a union of all these subspaces and closure must be equal to your entire whole space, that is concrete Hilbert space. And if you take an intersection, that must be trivial space. And third one will say for all j belongs to your integer set, then obviously Vj plus Vn is nothing but the one dilation of your Vj, that means the previous set. And similarly the fourth one, If f belongs to your v naught space, then obviously its translation must be belongs to the same space. And the last one says it is going to be that whatever the translation generated from the fourth property, that will forms orthonormal basis for your v naught. Okay, this is the conditions badly required to define a multi-resolution analysis. Now check one by one what this definition says. Let's have a look on equation 2, condition 2, that says bar of union of these must be equal to your Hilbert space. What that says? We know separable space, right? With a countable subset, then obviously the respective space will be separable, right? Are you understanding? Because I am speaking full of pure mathematics, right? Yes or no? If you speak, then only I can understand. Oh, you are listening. Yes or no? Yes sir. So therefore, this what the second definition says. That means that says the dense. That means if I consider this is whole hall is in L2 space, then except wall remaining as the union of this Vj, then if you consider if I one element from the Hilbert space, then obviously the remaining union will give one more element like me, look like same as me, with less than epsilon. With less than epsilon says that is just a difference will be very less than your epsilon. Choose an epsilon is however small, then the difference will still small. So therefore obviously another person will definitely look like me, right? Yes or no? So therefore that Hilbert space this says this is a dense means. So if you choose any element from the union of Vj, definitely from the Hilbert space there will be one element such that the norm will be less than epsilon, right? That's the meaning of dense. That means the closure is equal to all the space Hilbert space. Next. And the third one says, already I have told, just one dilation of Vj is nothing but your Vj plus 1. And if you close look into the your property 3, that says all spaces, whatever Vj plus 1 and Vj plus 2, they are uniquely determined. Because in each and every space, there will be a different orthonormal basis. We can define those spaces uniquely, not repeatedly, right? So therefore this is a multi-resolution analysis. By using this, we can obviously create some of the new wavelet bases. So next. So here is the one more property. We are using that. That means if from the multi-resolution analysis definition, the condition 3 and 4 has been satisfied, then the following obviously definitely holds. So that means the previous third condition says Vj plus 1 is equal to d of Vj, right? So now I am increasing the dilation, so therefore obviously this property will be holds. The Vj is nothing but the d power j of V naught. That means if I know the V naught space, definitely I can create V1, V2, V3, V4 by using this dilation d power j, right? Yes or no? So therefore next this is going to be then respective space. I need basis because there the space means every space there must be a basis. So obviously that span of dilation and translation parameter of your file will be acts as a basis for your Vj. So that means what? For every V0, for every V1, every Vj where j belongs to your integer, there will be a basis for every space. Okay? Next. So here our multi-resolution analysis, obviously whatever the condition they have given, because Har is a famous mathematician, already defined these, verified these functions are going to be orthonormal. So therefore psi is a characteristic function, and the Vj by using the previous concept, the f belongs to your Hilbert space such that the f is a constant, which is going to be characteristic function means is a constant, so which is defined in the support of that. Now this scaling function we are going to create in a wavelet. Wavelet always generated by the scaling function, not independently generated. Okay, so therefore here I am using this phi to create a wavelet. So by using the linear combination, the finally psi of x, this can be represented as a 1 by root 2 of this. So that means what? So we have expressed as a finite linear combination of scaling function as a wavelet, right? So that means so every wavelet can be expressed as a linear combination of your previous scaling function. R is the finite linear combination. Yes. Now, what is the relation between the Vj and one more space Wj? If you take Vj, if I take, let's say this is my Vj. So now from this Vj, I am taking one more small portion, let it be this one circle. Okay, this is the one whole circle, and in between that I am taking one small circle, and this small circle says V0, and this is going to be V. Because nested by the multi-resolution analysis, right? Then where is W? That is where is W? That means this is a V0 and this is a V1 means into V1 from the V1 remove this V0 is the main part into V1 W. So therefore W1 is nothing but the perpendicular space of V0 with respect to V1. Have you understood? So that means we can create, that means whatever the function we choose from the V1, with respect to that, if the inner product will be 0, then the respective function, two functions will be able to W1. That's what the Wj in this way is. So that's what I have written. The Wj is the element from Vj plus 1, where inner product of f comma g is 0, for all g belongs to your Vj. So whatever the element from the Vj satisfies the orthogonal property, then there will be element of your Wj. So in this way, we are going to create the Wj spaces. The Wj spaces represents the wavelet spaces. Okay? And here one more lemma. So with using the multi-resolution analysis, this lemma says, assume phi is belongs to Hilbert space and generates Hilbert space. Already I have told because multi-resolution has prepared on your phi. So therefore phi belongs to your Hilbert space with respect to multi-resolution analysis, and the psi is again belongs to your Hilbert space. Suppose because T psi is an orthonormal basis on what not that we are not, then obviously this is what are these properties is? This property is for each j belongs to that, then obviously I will get this one more set of your orthonormal basis, and those orthonormal bases acts for your Hilbert space. If it is j equal to 0, then it is just the W0. If it is 1, then it is W1. Similarly, so on. So that means for every spaces, we are going to creating orthonormal bases. Right? Yeah. No doubt. No voice. No voice. Then this and the function and this is now here I am using j. Now I am getting the j plus q. Now that will comes out from entirely fixed j. It is stick on for one space of spaces. Not if suppose I vary the thing, then it is extended to entire the space. It is called Hilbert. And now this function is the dj phi is the union dj phi, where j belongs to natural number. J are sometimes I consider z, sometimes I consider n. If I consider n and this union, this is forms your whatever orthonormal basis for your entire Hilbert space. Okay. Next. And this lemma 3 says, if I define some of the scaling function, how can I justify this is going to be scalar function? Right? To define scalar function, this lemma says if the n is if I want to say any function is a scalar, then it must be obeys the scaling function. The equation 1 represents scaling functions. So that means assume that the function if phi belongs to your Hilbert space, then generates a multi-resolution analysis. I am assuming that it is going to be generated multi-resolution analysis. Then obviously there exists one periodic function. We know one periodic function, which is period is one periodic function, let's say h naught. Again that function is also belongs to your Hilbert space, such that the equation 1 will be verified. So next, the proof is I have been written here, so not necessary proof. Okay, so now I am not going to emphasize on the more on proof, but equation 1 satisfies, then I can say, definitely I can say the phi will be orthonormal 5 will be the scaling function. Okay, the next. Now, we came to know that what is the necessary condition to say the scaling function. Now, by using those scaling function, I am going to define the wavelet orthonormal basis. So, by using that, we can generate this. That means any function satisfies this, then I can say, I can fully accept the respective function will be wavelet. Okay, what this condition says, this is emphasized by the previous theorem. Therefore, if suppose assume the phi is belongs to Hilbert space, generate MRA, and H0 already we have defined, and we have one periodic function satisfying the scaling equation 1 previously defined, and define one periodic function H1 by using your H1. Because I know H0, freely I can define H1. Yes or no? So H1, so therefore also define the function your side via this property, then the following is going to be holds, that is previous condition says about the scalar, now it says about the wavelet. So that is psi. So that means this, the translation of psi will form the orthonormal basis for your W0. Similarly, if you take a dilation, it will form orthonormal basis for the entire Hilbert space. Okay? Next. The relation of your V, the space spanned by the scaling function and space spanned by the wavelet function, that is H is equal to the W, direct product of W and W perpendicular. So we know that theorem. Direct sum. So therefore, that means by from the theorem of your Hilbert space, directly we can assume that so Vj plus 1 must be equal to the direct sum of your Vj and Wj. So this is the relation between the whatever the space generated by your scaling function and the space generated by your wavelet function. Okay. Next. Now, multi-resolution analysis. This is the one of the property. That means this theorem 3 says, if suppose any scaling function phi has a bounded support, then we have the following. So that means only finite number of scaling coefficients are non-zero. The first condition is, if beginning I have told, how to get a dominating coefficients, right? If suppose those phi defined in the bounded support, then obviously there will be only finite number of scaling coefficients. They are nothing but the coefficients, see there, right? So these scaling coefficients will be always the finite number of scaling coefficient, and similarly the corresponding wavelet psi according to MRA, the must be bounded support. If the phi is bounded support, obviously the psi is also bounded support. And if the phi is continuous differential of any order, then obviously psi is also continuous order of the same order defined for the scaling function. Next. Clear. So this is about previously we have say about how to create an orthonormal basis. Now wavelet obeys other than this property. What are those? The first one I call this is a vanishing moment. Number of moments going to be vanish. Number of moments going to be vanish. So what is this? Purpose of this is again, if suppose these are the orthonormal basis for your Hilbert space. If I choose one function from the Hilbert space, definitely those functions can be written as a linear combination of these bases, right? That's what I have written here, equation 2. Yes or no? So therefore this is equation 2 represents arbitrary function has been written as a linear combination of orthonormal basis generated by your Vj and your Wj. Okay? So this is represent your equation number 2. But previous lemma says this must be phi, right? Because phi is an orthonormal basis. Yes or no? So therefore now the problem with, not problem with this, actually problem with that. By previous theorem says if it is anything linear combination of your this orthonormal basis for your V spaces, then obviously there will be only dominating coefficient will be finite, right? So in infinite sum, this will become a finite. Now the problem with the second term. Okay, next. So now to reduce those dominating coefficients, to get only few number of dominating coefficients, I use threshold property. So next, I use threshold. This is usually done by the threshold. What do you mean by thresholding? That is, I choose the certain epsilon. So however small epsilon, which is greater than 0, and keep only coefficient in equation number 3 with satisfying equation number 4. So that means what? Whatever the function with respect to orthonormal basis obeys this property, that means greater than or equal to epsilon, then I choose only those number of elements as the dominating coefficients, and remaining I am neglecting. Okay, so in the remaining I am neglecting. So that means why I am neglecting? Because of this property. So that means in L2 of n, if this is an orthonormal basis in the Hilbert space, then obviously this series is going to be converged. Then obviously the coefficient is belongs to L2 of n. That means if it is belongs to L2 of n, means that must be a finite number of coefficients, because the series is a convergent. Series is convergent means the partial sum must be convergent. The partial sum must be convergent means the coefficient must be finite. Yes or no? So therefore in this way I can also reduce number of dominating coefficients as a finite number. So therefore with this vanishing moment I can definitely say if it is I use the wavelet, then obviously the coefficients, dominating coefficient will be finite number. Easily I can extract the information of the function f or any signal by using the finite number of coefficients, right? Next. And this is the definition of vanishing moment. This definition says if suppose any function has more number of vanishing moments, then obviously whatever the dominating coefficient will be less. Further, the decay of wavelet coefficients, next theorem says, this is the decay of wavelet coefficient. Why the wavelet coefficient is going to be decayed? Because of this relation. What is the equation number 5? The equation number 5 says, these coefficients will be less than or equal to this. That means what I have told, if it is n is more value, n is larger, that means number of moments is more number of moments, which is the vanishing moments, then 2 power infinity. If it is this tends to infinity, 2 power infinity, this is going to be 0. 1 by infinity, right? So the 1 by infinity, this is going to be 0 means these coefficients are less than or equal to 0. Okay, so that means so many number of coefficients are going to be nullified whenever the moments are more. Is it clear? So this is one of the beautiful property why we need to use wavelet. Next, and this cannot be seen by any other functions. Just remember that. And now, so this is orthonormality. From the beginning I have told you, the orthonormality is one of the best property to approximate any sort of the functions or any sort of the polynomials. Why? I know this is the theorem. This theorem says what? If suppose the S is containing a finite number of elements, which is going to be orthonormal basis for Euclidean space, let it be U. Then if the any vector belongs to this space, then obviously it can be written as a linear combination, right? Just remember, if it is linear combination, if it is expressed as a linear combination, then if I want to calculate each C1 to Cn, I need to use writing a linear combination and coefficient must be equating to left hand side, right? And we get a system of equation. On solving those equations, finally I am going to get it respective coefficient values. But if it is an orthonormal basis, you no need to calculate this. Directly it will say, just you choose whatever the wavelet and the respective coefficient will be inner product of this. Right, directly we can say. Next. So that means, next. Here, for example, I have chosen this is, same thing, if the A is a polynomial space with a normal basis, just one basis, let it be this is one of the bases, and the respective orthonormal basis is that. I have taken a two bases. Any space, obviously there will be a many number of bases, right? Yes or no? So for that one I have chosen, let it be this is a normal basis and that will be orthonormal basis. Then I will choose, let it be, because it is a polynomial basis having a dimension 3, at most polynomial of degree less than or equal to 2, so that's why I have chosen one arbitrary function belongs to your A. Now I need to express. So this is the one function, yes. I need to extract the values. What I need to do? Next. First procedure says, I am expressing in terms of the normal basis. linear combination and expressing and finally finding the respective coefficient and substitute here, finally I will get a 1 plus 2x plus x square. Okay, this is the way of procedure, right? If the same basis I replace it by orthonormal I approximated. Next, so this is just A can be linear product of this, that is nothing but 4 into root 2 by 3. Similarly, B is equal to this and C is equal to this. Now approximate, finally I will get this. Now tell me which one is the best way. If it is a finite, okay, I can calculate with paper and pen. If it is infinite, even more number of elements, then this is the better, right? So therefore, this is the way we can calculate the respective coefficient. If I use orthonormal basis, not simple basis. And one more property is there. If I choose x power 4, is it x power 4 previous? Is it x power 4 belongs to your A? Is it x power 4 belongs to A? Belongs to A? Because A containing, it is a polynomial space having a degree at most less than or equal to 2. It is a order 4. It doesn't belong to A. Is it possible to approximate this sort of the function by this basis? No. If you approximate operator, definitely you are going to get a 0, 0, 0, 0. But the orthonormal basis, you don't worry. I will express that function. Next. So here, I use an orthonormal basis. So I have got this is a root 2 by 5 and similarly 0 and 4 into root 2 by 7 by root 5. Then I approximated, finally I got this is the value. Now x power 4 minus this is an absolute value. But previously the basis given, normal basis given 0. All coefficients are 0, right? But here up to 2 digits, the respective function x power 4 is approximated by this orthonormal basis. That means if suppose the respective function may not belongs to the respective space, then using the orthonormal basis we can identify which sort of the function we have utilized. Right? So this is another beautiful property of your wavelet. Next one, compactly supported. The compactly supported says support means where the function is defined is not equal to 0. That is the support. Compactly support means we know closed and bounded, right? So compactly support means compactly support is nothing but a closed, least closed subset containing the support of the respective function. We know if it is a once defined function is compactly supported, then that function will satisfy many of the properties like as a differentiable, continuous and continuous, right? If it is a compactly support, definitely I can use those properties of a uniformly continuous, and more than that use and for your wavelet function. Okay, so this is about wavelet, how to create the wavelet and what are the properties we can use. With these properties, now the wavelet is armored stage. Now it is ready to apply to get a desired solution for some of the differential equations, right? So here this is one of the polynomial wavelet. I skip this. Directly I move to the application. Okay. So here the polynomial wavelet on the interval is defined by using your Chebyshev polynomials, first and second kind. And next, here I have defined your psi jl of x is a scalar function. Next, this is going to be your wavelet function. So I used continuous polynomials, right? By using the continuous polynomial, Chebyshev polynomial, I have framed the respective scalar function and respective wavelet function. And these functions, if I want this is a wavelet, there must be orthonormal basis, right? Yes or no? That means that it has been written as a Wj, product sum of W1, W2, W3, similarly so on. Yes or no? The next. So here, this Wj for every j and l. And one more thing, if the j of this is going to be orthonormal, that means if the k and l is not equal, then this function is crosses x-axis. In the beginning definition I have told, so it must be waving off x-axis over and below. Yes or no? So therefore, this oscillating over the x and x axis, and this is the Wj, which is span with respect to this function, and varying the j, take product sum, then finally that will be equal to your Hilbert space. Okay, so therefore here in continuous variate also we have generated the orthonormal basis for each and every spaces, right? So next move to the application. I won't take much time. Within 5 to 10 minutes I will finish. Next. Operation matrix. In wavelet, you choose if operation matrix means we can define, I can apply the series method, operation matrix of integration, operation matrix of differentiation. I prefer always operation matrix of integration. Why means small number of coefficient can be predicted by using the higher order degree polynomial. So that's why I always prefer your operation matrix of integration. Now using whatever the function previous. So by using whatever the wavelet function defined with respect to collocation point previous. I use this is a collocation point for this wavelet function. I am generating the operation matrix of integration. Next, this is the H represented, that means a wavelet representation in the matrix form. Next, it is first operation matrix, that means a one-time integration of the respective wavelet function. Next, second twice integration of your operational matrix. Next, then similarly for the particular 3x3 matrix, I will get this. Okay, and this is the method I applied. So for simple PDA, I applied this method. I will consider the plain Gordon equation which having the initial conditions this. Now this is my approximation. This is my approximation means in this problem, I need to calculate y with respect to t twice. I need to calculate y with respect to x twice and y. So therefore, I to get a dou y by dou x, I integrate with respect to once, with respect to x once. Then I get next. Then I get next. Then I get this, and this is nothing but a matrix representation of this. That means this is I got. I need to calculate in the matrix representation. This is a purely function of t by using the given collocation point represents M1 as a matrix 3 by whatever the size you have chosen. And similarly, I will calculate the y, and this is a matrix representation of y. Next, and I need y with respect to t twice, and finally differentiating the y with respect to t twice and putting it into the matrix form. I will get a 14 and 15. What are the equations required? Substitute the given equation. Finally, you will get a system of equation solved by Newton-Raphson, and you will get unknown coefficients. Those unknown coefficients substitute in y. Okay, and remember this d1, d2, d3 are the operational matrix of differentiation, because I have derivative, right? So therefore operation matrix of differentiation. In the same way of integration, just use the differentiation. Next. So here I am going to apply, this is one of the example I have chosen. This is the problem I have taken. Next. It has the exact solution. The y is equal to y of x comma t is equal to square root of 2 by 3 tan. Next. Here is the solution we have got. When with the high j value, when you vary j, then only wavelet come into the picture. If you fix it 1j, it is not a wavelet. It is just one space of the, you are defining a subspace in the subspace, not entire Hilbert space. So that's why you need to vary the j. Let's say if the j is 4, here I have chosen j is 4, then the absolute error will be 10 power minus 6. If you increase j value, it is, I have considered in, for the j is 6, 4, j is 6, then the absolute will be 10 power minus 10. That means when j increased, then the accuracy of the solution also increased. But if you see the surface plot, they are looking same, right? But you observe in the absolute error, there we can identify where exactly differ. And similarly next, and why we need to use wavelet? Wavelet similarly you apply for any differential equations which are having a smooth function as a solution, definitely it works. If it is sum of the which is a polynomial of degree finite, then it is gives exact solution. Nothing to worry. But wavelet can give the accuracy at where the sharp edges, sudden jump, there actually this wavelet works. That's why they have created our wavelet. So, but we are using for any, for all sort of the differential equations. Here you see, this is an exact solution. But now we applied the wavelet method, so it is exactly giving the information of the respective sigma. Right? So therefore next is a numerical comparison. I have compared with other numerical results existing in the literature. So this is our errors with respect to L2, L2, L infinity, similarly so on. So this is for different value of, just to check for j is equal to 4, this is an absolute error with the exact solution we have got. So accuracy when j is equal to 4, I am getting a 10 to the power of minus 9. Similarly, when j increased, next, then j increased, let's see, the accuracy also increased. So that's why I am saying use j vary, then you get the power of your variance. If you fix it j, then you won't get like as a similar polynomial solution. Okay, so this is about my lecture. So if you have any doubt, please.
Anybody have any questions regarding wavelets?
Sir, namaste sir. Your lecture was very good, and I have already met you during the conference in BCU, and there, since I was second year PhD students there, lot of questions which was running in my mind regarding the initial wavelet questions. You have solved that, but now my question is that not regarding this PPT, but one of your paper regarding Hermite wavelet. There you have considered k equal to 2 and m equal to 3. My question is that when we consider the boundary layer theory flows, and when we apply, when we consider viscoelastic fluid which consists of highly nonlinear term like coefficients f into f power 4, just by considering k equal to 2 and m equal to 3, we will get only 6 basis functions and operational matrix of integration, only those. Is it sufficient to consider only those number of wavelet coefficients, or we need to consider the highest number of? Yes, sir.
Accuracy.
Yes, sir.
If you apply this series technique or operation matrix, there will be a certain region. After the certain series, it will diverge.
Okay, sir. Thank you so much, sir. And when we consider this, apart from k equal to, that means for large number of k and m, we will get a huge matrix, and that cannot be solved manually. So we have to go for coding purpose only.
Coding purpose.
Yes, sir. And the stability, what you said just now, the stabilized property.
Is that same with respect to fluid stability what we...
No, it is different from that.
Okay, sir. Thank you so much.
Any other questions? If no questions, I would like to congratulate Professor Kumbhi Narsaya and on behalf of the organizing committee of the KC Karnataka University, and thank you very much. Thank you very much for your work.
Thank you very much. Thank you very much, Dr. Kumbhinasar sir, for your wonderful talk. And also I thank Dr. Vijay Girisha sir for chairing the session. Now there is one group photo session, so I request
volunteers cheer after all participants, voice participants.